this video, we're going to look at the displacement in a physics situation where there is possibly an initial velocity, but where acceleration is present. So let's just get going. Let's get right into this. We started off our work with physics with the understanding that we could find a final position, which we use the variable d sub f as final distance, because that position is oftentimes, or can be, it can be referenced based off of its position relative to a position, so the distance from a reference point. So the final distance from a reference point is how far was it from the reference point to begin with, plus how far did it move. And then we went on to define this delta D as the rate at which it was moving times how long it was moving. So delta D ultimately became delta D equals what is the rate at which it's moving, which we're gonna call velocity, times t. And it's the average velocity. When we began working with this, we simply called it velocity, and as we progressed, we came to understand that we have to deal with this term as the average velocity, because, for example, if I drive from here to Indianapolis, I'm not going to have a constant speed the whole time, but I can find my average velocity by taking the distance and dividing by time, and that's going to give me the average velocity. So we expanded our understanding of this concept. So with that in mind, the next thing we went on to do was look at the effect of acceleration on velocity. And so we said the final velocity is how fast is something moving plus how much did it change. And in a parallel to this, we said that the change in velocity is equal to the rate of acceleration times time. Now, as we move forward, the next logical thing in this progress is, how do we calculate a final distance when acceleration is present? And in order to do that, there's a little algebra that we can go through, a little algebra exercise that will lead us to that. I know that some people are going to immediately want to skip. So I will put in the time code where you can skip to the example problems. So here's the algebra. All right, here's the algebra that we need to go through in order to get to the final displacement in the case where acceleration is present. So the algebra begins with final distance equals, that's a terrible D, d sub I plus the average velocity times time. So how are we going to come up with this average velocity in a case where the velocity is changing? Well, that's easy enough. There's an equation for average velocity, and it says V av, the average velocity, is the initial velocity plus the final velocity divided by 2. How fast was it going? How fast was it going when it stopped? Add them together, average. There's your average velocity. Now we can go back to this final velocity, because on the page I threw away, we had the final velocity is the initial velocity plus the rate that it accelerates, and how long does it accelerate. So we can take, this is where I love my color highlighters, I can substitute this equation for V sub f. Algebra. This is big fun. So the average velocity becomes the initial velocity plus this, which is VI plus AT. Boom. Now, I'm going to combine terms, and I'm going to separate it. That's a 2. I don't really know what language that's a 2 in, but we're going to go with it being a 2. Now I'm going to split it. 2VI over 2 plus AT over 2. The 2's are going to cancel, and I'm going to end up with VI plus, and I'm going to bring the 1/2 out just because it's more commonly seen this way. And here we have the final equation. So I split it, and now I end up with a average velocity term that relies on the initial velocity, the rate of acceleration, and how long it accelerated. Very simple, right? All right, now what? Well, let's put this little piece up here at the top. Move my... And I'm going to go back to that final distance equation where we said d sub f equals the initial distance plus the average velocity times time. And doing the same algebra technique, I can take this term, here, plug it in for average velocity. What? So d sub f equals di plus all of that times t. So what is the all of that? Here's the all of that. I'll get my highlighter going again. Got the average velocity there. So what is average velocity? Well, that is average velocity. VI plus 1/2 AT. That's a T. Now I'm going to multiply the T into the parenthesis. So I have the initial, how far is it from the reference point to start with, plus VI times T plus 1/2 AT times T. And this now becomes our position or distance equation that accounts for not only the object being some reference distance from the reference point, and it's moving with an initial velocity and it's accelerating. This is the only equation we're going to need in order to solve where something is. If there's no initial velocity, this term becomes 0. If there's no acceleration, this term becomes 0. So if there's no velocity and no acceleration, how far is something from the reference point? How far is it? That's it, d sub I. If there is no d sub I, if the reference point is the origin, like a runner on the track begins at the starting line, and then 5 seconds later, how far are they from the starting line? D sub I is 0. That term goes away. If there's no d sub I and no acceleration, we end up with VIT, which is back to the how fast is it going times t. It's not that hard. It's an ugly looking, it's not that ugly, but there's a lot of terms. And this is why we have to go through the 3 steps. This is why we have to go through the steps of what's given, what equation are we going to use, plug in the numbers, and then do the math. And if you otherwise, if you don't memorize, if you don't use this equation, you're going to have to put together a bunch of different equations. So the only other piece that we don't have is what is the final velocity? And final velocity is the other equation we need. V sub f is vi plus at. Now these two equations are gonna cover almost every case of everything that we need, unless you're just flat given the initial velocity and the final velocity, in which case then the average is vi plus vf divided by 2. And rarely you'll be given like something is a distance from the reference point and it moves 10 more meters. So then you could have d sub f equals di plus delta t. And then the same case with velocity. V sub f equals vi plus delta v. You're not going to see these kinds of questions very often. You're not going to see these very often, but occasionally. And so our entire repertoire of physics equations boils down to this, and then these three, occasional equations. So 5 equations, and we can handle the physics of motion from start to finish. That's a 12-minute video. We're going to call it. I'm going to call it.